Okay, so let's talk about chemical formulas. There's actually quite a few different kinds of chemical formulas. For now, the two most important ones that you're going to look at are molecular formula and empirical formula. So we're quite used to molecular formula. These are the things we've been writing. You're supposed to have been learning about them grade 8 and grade 9. So when we write the molecular formula, and the molecular formula is like H2O, NaCl, like that, but actually molecular for molecules. There's another particular name for it for ionic things, but we won't go into that just now. But the molecular formula, you know, H2O, CO2, O2, H2, that's the actual number of particles in the compound, and we write the letter from the periodic table, which symbolizes the element, and the subscript, the small letter at the bottom, small number at the bottom, is exactly how many of each of those atoms we have. So this is the normal thing that's used most of the time in chemistry, but sometimes we have what's called empirical formula. Now usually empirical formula comes actually out of doing experiments, because everything in the periodic table's got a different mass. So if you have reactants go to products and you check out the masses, you can actually find the ratio of elements, but you don't actually know exactly how many atoms you've got, and so you can form a chemical formula because you know what elements you've got and you know what ratio they're in, but you don't know exactly how many per molecule. You just know their ratio. Okay, so for instance, things that would have an empirical formula would be like this. This is a diamond, and we're just going to write the letter C. We don't actually know how many atoms there are, but it is only carbon. And silicon dioxide, this is an empirical formula because we don't actually know how many atoms there are, but the ratio is 1 silicon to 2 oxygens. Okay, so they're similar, but they're not exactly the same. So this to me is the easiest way to figure it out. This would be the molecular formula of a bunch of compounds, okay, and this would be the empirical formula. So if you look here, P4O10, if we divide by 2, we get P2O5. Okay, can you see that? There's a mathematical relationship. So this is the simplest ratio that this formula can be expressed as. So P4O10 would be a molecular formula, but the empirical formula would be P2O5. Now if we look for instance at water, water is actually, if we cannot divide through to make this simpler and still get a whole number, remember we can't get half an atom. So H2O is the molecular formula, H2O is the empirical formula. This is going to become important later. We're going to do calculations. Now this chemical is called dinitrogen tetroxide, N2O4. Can you see 2 and 4 have a common factor of 2? We can divide through and find NO2. This compound could be almost anything in organic chemistry. This thing can actually have a lot of names in real life because this is an organic compound. But we've got 10 carbons and 22 hydrogens. Can you see the common factor is 2? So its empirical formula will be C5H11. Likewise, this thing, which looks a little bit like glucose, this thing has got the formula C6H18O3. If we look here, 6, 18, and 3 have a common factor of 3, so its empirical formula would be C2H6O. Remember, there's an invisible 1 there if you really want to think about it that way. But then if we look at C5H12O, prime number, there is no other simpler formula, so this molecular formula is exactly the same as the empirical formula. So some compounds have both a molecular and empirical formula, some don't. It's just, but this is what it's called, and you need to know this is an empirical formula. It's the very simplest ratio that a molecular formula can be expressed as. Now, the last kind of way of representing, well, it's not for now, it's the last way of representing them, is the structural formula. And this is very, very important in organic chemistry, okay? And so when we get to organic chemistry, we're going to learn more about this. And next year, like I said, when we do the valence shell electron pair repulsion theory, we'll learn why people draw large structures with this weird three-dimensional shape. Okay, so for instance, this is glucose, which has got 6 carbons, 1, 2, 3, 4, 5, 6 carbons, and then 12 oxygens, 1, 2, 3, 4, 5, 6, 7, 8. There's a couple behind them. You obviously can't see them. the hydrogens behind there, and then the 6 oxygens, 1, 2, 3, 4, 5, 6 oxygens over there. Okay, so this formula actually, if we're doing organic chemistry, doesn't tell us very much, but this formula will tell us a lot. So for instance, there are things that have got similar formulas but that are not the same. So if we had, for instance, acetic acid, which is vinegar, we would draw it actually like this, and when we get to grade 12 we're going to be doing this a lot. There's a lot of structural formula drawing. So we say here are the 2 carbons and they are bonded to 3 hydrogens, okay, but this carbon is bonded to 2 of the oxygens and 1 of these oxygens is bonded to the hydrogen. So from this formula here you can't tell that there's an oxygen bonded to a hydrogen, okay. You can't tell is the hydrogen bonded to the oxygen or is the oxygen bonded to the carbon. And that is why you need the structural formula. The same way with this formula here, we've got 2 carbons, 6 hydrogens, and an oxygen. What does this actually look like? Where is the oxygen? Is it in the middle? Is it on the ends? We don't know until we draw the structural formula. So this is really important in organic chemistry, but not so important for us now. You just need to know it must exist. And then you must know ways that we can show compounds. Okay, so obviously when we use our chemical formula, it's a representation of atoms. So NaCl is a representation of table salt. Okay, so we can use formulae, which we're familiar with. You saw some diagrams on the other page, and then there are obviously models, 3D models, and you know I have some of these in the class made with my balls and my toothpicks. You can actually buy little kits like this that show you the 3-dimensional representation of atoms, and you can only stick the sticks in the correct orientation. And these kits are very expensive and they're quite small, the things. They're not good for looking at. So that's why I've got my things with the toothpicks. But if you've got a lot of time on your hands, and you are Sheldon Cooper from the Big Bang Theory, for those of you who don't know what I'm talking about, if you look in their apartment, there's actually a complete, correct molecular model of DNA in his house. So this is actually these little ball and sticks made into DNA. So you can see you can make large structures. Okay, so for instance, here are some representations of this organic compound ethane. So here's what the Lewis dot, which we know. Can you see the carbon has got its valence electrons, and then the hydrogen is sharing the electrons with it over here. Okay, so there's 1, 2, 3, 4 electrons from this carbon, and 1, 2, 3, 4 electrons from that carbon, and then the little gray electrons are from the hydrogen. So this is Lewis dot. This is what we call ball and stick, where every stick is a chemical bond, and if there's a double bond we usually draw 2 sticks, ball and stick. So that's a ball and stick model. Here is its molecular formula if we were to write it down, C2H4. But if we had to write this as an empirical formula, it would be CH2. And then finally, sometimes we have another way of representing it, because this is very useful for understanding intermolecular forces. We actually draw the electron clouds, and the electron clouds give you an idea of the structure of what it actually looks like, because this looks like a bit long and skinny, but when you look at the space filling model, it's not so long and skinny. So all of these have different uses for when we want to represent different things, and you need to be familiar with them. And if you can form these mental pictures in your brain of compounds, it really helps you understand bonding and how chemical reactions occur. One thing I must warn you about the space filling model: if you see a space filling model, you can't tell how many bonds are in here. So say for instance there could actually be a double bond in here and you won't know it. That's the advantage of the ball and stick. If there's 2 sticks, there's 2 bonds, and so that's one of its advantages. So here are some more examples. Here's water's Lewis structure. Here's water's space filling model. Here's water's ball and stick, and here is a geometric sketch. And they do actually know that the angle between the 2 hydrogen atoms is 105 degrees, and that's something we look at next year as well. If we look at ammonia, this is a space filling model of ammonia. Here is one of the ball and stick ones. Here's our Lewis dot for ammonia. And here obviously is the NH3, the chemical formula. So there are all these different ways of representing things so that we can explain things easily in chemistry. Okay, so the next part of this comes to how do we know if we've got an element or how do we know we've got a compound? When I tell you that water is made out of 2 hydrogens and 1 oxygen, you like look in your glass of water and you like, somewhere it just looks like water. How do I not know that this is not just one atom? And this is where we go next with chemical reactions to know whether we have a compound or an atom or an element or whatever it is. So I will talk about that just now.